Hi, I'm Cody Smith, Technical Support Manager for Cloyes Gear and Products. Cloyes has over 95 years of experience focusing on one product line. We have supplied kits and components for both the automotive aftermarket and original equipment manufacturers. These products can be found at some of the largest distributors and retailers across North America as well as internationally in over 24 countries throughout the world. In today's video, we are providing a general overview of automotive timing drive systems. We will be looking at examples of timing systems across different engine types, learning timing system terminology, and we'll be discussing some important aspects of the various components. An engine's timing drive system is the term used to describe the components that connect the engine's crankshaft to its camshaft or camshafts. Shaft timing is important because incorrect timing can cause poor performance or even piston-to-valve contact. The connection of the shafts can be done in a few different ways. In the automotive world, one of three options are used: a chain or multiple chains, a belt or belts, or gears. All these systems are intended to maintain proper crankshaft to camshaft angles during rotation. Let's start by going over the different types of engines you will encounter. The first engine type we will discuss is overhead valve or pushrod engines. This design uses a single camshaft through the center of the engine, which indirectly drives the valve train using lifters and pushrods. Because the camshaft is through the center of the engine in this design, it is in close proximity to the crankshaft, therefore only requires a short timing drive system. Although examples of tensioners and/or guide assemblies can be found, like on this GM Gen 4 engine, all pushrod engines use a simple three-piece set, including a crankshaft sprocket, a camshaft sprocket, and a timing chain. The other commonly found option for overhead valve timing drive systems are gears. Gear drive systems are typically found on diesel, classic inline automotive engines, and other heavy-duty applications. Note, in all four-stroke engines, the crankshaft and camshaft operate at a 2-to-1 ratio, the crankshaft spinning twice for every one camshaft revolution. Because of this, the camshaft sprocket or gear will always have twice as many teeth as the crankshaft sprocket or gear. The next engine type to discuss is single overhead cam. As the name suggests, a single camshaft is placed over the top of the cylinder head that operates both the intake and exhaust valves per each bank. Because of the long distance between the camshaft and the crankshaft, a more complex drive system must be used. This can be achieved through the use of a single long chain or belt, multiple chains as shown here on our modular Ford V8, or one of many combinations of belts, chains, and/or gears. The addition of spring and/or hydraulic tensioners along with chain guides also becomes necessary with the long distance between the shafts. Tensioners and chain guides on a chain system and tensioners and idlers on a belt drive system stabilize the drive system for consistent timing and longevity. Double or dual overhead cam engines are the final engine type we will discuss. Dual overhead cam engines are similar to single overhead cam design, except there are separate camshafts dedicated to intake function and exhaust function. In V configuration engines with 4 camshafts, multiple timing chain systems are typically used, including a primary system and 2 secondary systems. The primary system will always be driven by the crankshaft, while a secondary system drives the camshafts. Similar chain systems are used on inline configurations, but with only 2 camshafts on a single head. You can count on each chain having its own tensioner and guides. The use of an idler or accessory drive sprocket is also prevalent in these systems. Variable valve timing on dual overhead cam engines allows for the most crankshaft to camshaft valve event control of all designs. Therefore, dual overhead cam designs will continue to be widely used across all manufacturers. What is variable valve timing, you may ask? Variable valve timing, or variable camshaft timing, commonly referred to as VVT or VCT respectively, is a technology that allows a camshaft to be advanced or retarded relative to crankshaft position variably across an engine's RPM range. The technology is used in some capacity by most manufacturers. VVT systems use a cam phaser or actuator, which is a 2-piece sprocket design, on the camshaft nose instead of a standard 1-piece cam sprocket. Using the engine's oil pressure through oil porting, controlled by a solenoid and the engine's management system, the phaser has the ability to advance or retard cam timing. By using this technology, manufacturers are able to tune engines for fuel and emissions requirements while maintaining horsepower and torque demands. Engines can have a single phaser, dual phasers, or quad phasers with the ability to control a single camshaft individually or multiple camshafts independently depending on the configuration. With the complexity of VVT system components coupled with multi-piece timing systems, a high potential for misdiagnosis is created. A lack of oil feed to the phasers due to worn cam journals, poor oiling system health, clogged oil passages, or component failure can cause timing chain system instability. Proper diagnosis of the root cause for chain instability is key to a successful repair. Let's now go over some of the components with a little more detail. We will start with tensioners. Timing drive system tensioners can refer to hydraulic units with a spring, or spring-only units, all with their main function to tension a timing chain or belt. Timing system tensioning is necessary to stabilize and absorb system harmonics during operation. Tensioners will also provide a range of operation to endure chain or belt fatigue life. Some chain drive systems utilize a leaf spring nylon tensioner to apply pressure to a chain. Other systems use the engine's oil pressure to operate a hydraulic unit that pushes against a tensioner shoe. Timing belt system tension may be set manually, may use an independently charged hydraulic unit, or may use an automatic belt tensioner. Tensioners can have multiple features unique to a specific application, so it's important to research the application and follow installation instructions. These features include internal or external ratcheting mechanisms that may require a specific activation procedure after installation. Ratcheting mechanisms provide a mechanical limit to the hydraulic range of motion of a tensioner. This mechanical limit is vital during low oil pressure situations and at startup. Healthy oil pressure and quality is also imperative for hydraulic operated units to function as they are intended. Never use any kind of RTV silicone or gasket maker on a hydraulically operated tensioner, as it can clog inlet oil passages. Tensioners are manufactured with finished surfaces that require no gasket, have a built-in gasket or O-ring, or they may include a separate soft metallic gasket. It's also important to torque attachment bolts to specification to avoid warpage to the tensioner housing and to prevent leaks. There are two main designs of chain found in automotive applications. They are roller and inverted tooth. Roller chains use a roller to engage with sprocket teeth to eliminate drag. Roller chains are identified by pitch, number of links, and roller diameter size. The pitch is the distance from the center of one pin to the center of the next pin. Typical pitches for automotive roller chains are 3/8, ½ inch, 7 mm, and 8 mm. The number of links is easily obtained by counting the links around the chain, including the interconnecting links, or just counting the outer links and multiplying by 2. Typical roller diameters for automotive chains are 250 thousandths, 335 thousandths, 4 mm, and 5.65 mm respectively. Inverted tooth chain, or also referred to as silent chain or link belt chain, is another chain design used by manufacturers. They are made by lacing a series of links connected by pins. This design has been proven to be a durable option implemented by manufacturers to reduce noise and vibrations. This is done by utilizing profile engagement between the chain and the sprocket. An inverted tooth chain's pitch and number of links are found using the same process as roller chains. Timing chains in some applications have marked chain links that align to sprocket timing marks for the installation process. Chains can have multiple marked links depending on the application to align to sprockets of a drive system. Timing chain guides can be found in a variety of shapes, sizes, and materials. Stamped, cast, or reinforced nylon bracketry is used to typically mount a nylon chain contact surface. Chain contact materials are designed to resist wear and provide a low resistance surface for the chain and should last the life of a system. Damage to a timing chain guide is typically the result of another issue in the system. Instability in the system caused by chain fatigue, a lack of lubrication condition, or a tensioning or variable valve timing system problem will cause damage to the chain guides. Sprockets are also found in a variety of materials and designs. Billet steel, cast or ductile iron, forgings, and sintered metals are commonly used materials in sprocket production. Sprockets are not only used to drive an engine's crankshaft and camshafts. Examples can be found in various applications where water pumps, balance shafts, oil pumps, and idlers are driven by a chain sprocket system. As stated earlier, sprocket teeth must be designed to work with specific chains, and timing marks are commonly found on the front of the sprocket for installation purposes. Sprockets typically feature a dowel hole or slot, a keyway, or an indexing feature to ensure proper shaft engagement for proper shaft timing. Sprocket indexing features are not designed to withstand torque loads from the timing system, only to set proper shaft timing until the sprocket is attached by its respective bolt or bolts. The clamp load created from the sprocket's attachment bolt is what holds the sprocket to its shaft. Before closing, here are some key points I want to address. Replacement intervals can be found for timing belt equipped engines and should be followed strictly. Refer to your owner's manual for timing belt replacement recommendations. Timing chains, on the other hand, are generally considered internal engine components and are not given replacement intervals. With that said, timing chains are prone to meet fatigue life during an engine's life cycle, and hydraulic tensioner function can weaken over time. The replacement of the complete timing system is always recommended over replacing individual components, especially when addressing a component failure or issue. When a component fails in a system, stresses are increased on all system components. For example, a fatigue chain can work a chain tensioner past its operating range. This can allow for chain instability in the system, resulting in chain guide and sprocket tooth wear and/or possible tensioner damage. The only exception to total replacement is the possible reuse of sprockets with our available sprocketless kits. There is no universal way to time an engine. Every engine has a specific, often complex procedure to set the engine's timing. Special tools may be required to set and/or hold shafts during this procedure. Some applications require aligning marks to static locations on the engine's block or head. Some align sprocket marks to other sprocket marks, and some applications use marked chain links and sprocket timing marks to align the shafts properly. Thanks for watching our overview on automotive time and drive systems. If you have a question about a topic we discussed in this video or any other timing related question, feel free to contact our tech line for assistance. Also note that Cloyes has a series of installation videos on specific applications available at cloyes.com or through our Cloyes channel on YouTube.